According to simple harmonic equation, energy is equal to 1 by 2m x naught square omega square, where m is the mass, x naught is the amplitude, omega is the angular speed. So in simple harmonic motion, omega is constant, m constant, 1 by 2 value is constant. So when this portion, this and this constant, we can write energy in simple harmonic motion in oscillation is x naught square, mean energy directly proportional to amplitude square. Now this relation can be written as energy 1 over energy 2 is equal to amplitude 1 square over amplitude 2 square. Now, energy is lost during oscillation due to some resistive forces. In the case of the pendulum, resistive force is air resistance. So when pendulum overcomes resistive force, its energy total decreases, which has direct effect on its amplitude, which also decreases. Now, due to the scare, the decrease in the amplitude is not linear. It is exponential, mean non-uniform. So, if the energy is E, amplitude is A, when amplitude decreases by 2, then the energy decreases by 4 due to the square of the amplitude. So this decrease is not uniform, not linear, so it is called exponential or non-linear decrease. And this decrease in the energy and its result on the decrease in the amplitude is called damping. So this process is called damping. So what is damping? Damping is actually gradually decrease in amplitude of an oscillating system due to loss of energy while overcoming all resistive forces is called damping. So this is the definition of damping. So gradually decrease in the amplitude of an oscillating system due to loss of energy while overcoming all resistive forces is called damping. And we have done this is non-uniform process. For example, this is displacement, this is time, and the maximum displacement is amplitude. When the pendulum is released, it is oscillating like this. Its amplitude is gradually decreasing. Look, it is decreasing gradually. And this phenomena is called damping. And do remember, during damping, mass, time period, frequency, and omega all remain same. So if this is 0, if this is 2 seconds, then this will be 4 because the time period remains same. So during damping, only the change in amplitude, no change in mass, no change in time period, no change in frequency, no change in omega, because the omega square depends on G over L or K over M. So G constant, length of the pendulum constant, material of the bob constant, mass constant. So during damping, only amplitude decreases due to decrease in energy. Okay, now suppose example of the pendulum. If the initial energy of the oscillating system is 15 millijoule when its initial amplitude is 5 centimeter, after losing 20% of energy due to resistive forces, what will be new amplitude? This is the question. Now, we have done that energy is directly proportional to amplitude square. And this is the equation. So we will use this equation. Energy 1 over energy 2 is equal to amplitude 1 square over amplitude 2 square. Look, the initial energy E1 is 15 millijoule. Now the question is, what is the remaining energy after 20%? So the remaining energy is 80% of 15. So 80% of 15 is approximately 12. And then the initial amplitude is 5. So we will write here 5 square. The new amplitude is required. So 15 divided by 12, 25 over x square. So we can write x square is equal to 25 multiplied by 12 divided by 15, and then the under root of this whole here. So the x answer will be 4.5 centimeter. You can check with the calculator. So this is the new amplitude after losing 20% of its energy. This is the calculation. But if the graph of any energy is given, like this is the graph, this is the energy, this is positive displacement, negative displacement, mean position, and the graph is posed like this. This is the graph for the kinetic energy. So this is kinetic energy graph. This maximum energy is 15 millijoule, and this displacement is 5 centimeter minus 5 centimeter. And the question is, solve this, attempt the same question with the help of this graph. So this is energy. Which energy? Kinetic energy graph. So what is the relation of the kinetic energy with amplitude? When amplitude increases, kinetic energy decreases. Look, When amplitude is increasing, kinetic energy is decreasing. At the maximum displacement, maximum amplitude, kinetic energy becomes zero. So instead of the remaining energy, we will use here the lost energy. So what is the lost energy? Why lost energy? Because the kinetic energy is lost with amplitude, with the gain of amplitude. So the lost energy is 20% of 15. So 20 divided by 100 times 15. So this is 3 millijoule. So this is the lost energy, 20%. So we will draw here lost energy lines. So this is 5, this is 10. So 3 will be here. We will draw here a straight line at the lost energy. And then we will find the intersection point. These are the two intersection points. When we will read these 2 points, definitely they will be 4.5 and minus 4.5 on the graph sheet. So whenever we have to attempt this question with the help of the graph, kinetic energy graph, so we will use the lost energy, because with the increase in amplitude, with the gain of the amplitude, kinetic energy decreases. So when you will draw the line, horizontal line, exactly at the lost energy, then you will get the exact value of 4.5. Okay, now if the graph is not kinetic energy, this is energy here, this is displacement, this is the mean position. If the graph is like this, and this is the maximum 15 millijoule, and this maximum displacement is 5 centimeter, this is here say minus 5 centimeter. This is potential energy, gravitational potential energy graph. Now, when amplitude increases, potential energy due to the height also increases. So here, instead of the lost energy, we will use here the remaining energy. So after 20% loss, what is the remaining energy? It is 12 millijoule, already done. So we will draw the graph at 12 millijoule. So this is 5, this is 10, suppose this is 11, this is 12. So here we have to draw a straight line at the 12. Now it is intersecting the first graph at 2 points, and we will find the value on the graph. So you will get the same 4.5 here and the minus 4.5 here. So if kinetic energy graph, lost energy line. If potential energy graph, then remaining energy line, then we will calculate the exact answer for the new amplitude. Number 1 is the light damping. Okay, this light damping is actually due to small resistive forces. In this type of damping, object completes more than one oscillation. So एक से ज़्यादा oscillation complete हो जाती हैं. For example, pendulum is displaced from this position. When it is released, it is oscillating like this, amplitude gradually decreasing. This is first complete oscillation. This is second. So amplitude is gradually increasing and more than one oscillations are completed. So this is the example of light damping. If more than one oscillations are completed by the object, this is known as light damping. Like pendulum, pendulum is oscillating, it is overcoming the resistive force, but before stopping, it completes several oscillations. So this type of the damping is called light damping. Now the problem is, in all damped motion, we can't apply equation x is equal to x naught sine theta, v is equal to x naught omega cos theta, and a is equal to minus x naught omega square sine theta. We can't apply because these equations are only applied when amplitude is constant. When the amplitude constant, then the system is called undamped system. So these equations are only valid for undamped system. So here in this type of the oscillation, which is called the damping, we can't apply any equation. Now, this x is equal to x naught sine theta cannot be applied. Number one, amplitude is not constant. And number two, this is not sine theta graph, this is a cos graph. So there are two reasons, right, for this equation not valid for this. Number one, x naught is not constant, mean amplitude is not constant, we can't apply. And number two, this is not sine graph, this is the cos graph, because the motion is started from the extreme position, not from the mean position. Okay, so the next equation is x is equal to x naught cos theta. This is a cos graph. Can you apply this cos? No, we can't apply. This is cos graph, but this is a single reason that the amplitude is not constant. Okay, if the amplitude constant for this graph, we can apply x is equal to x naught cos theta, but here it is undamped system. No, it is damped system, right? So for damped system, no equation is applied. No equation is applied for this type of the motion, which is called damping. So the light damping, in which more than one oscillations are completed, due to the damping process, we can't apply these equation. This is cos graph. So sine graph or sine equation cannot be applied due to two reasons. One, the amplitude not constant. Number two, motion is started from extreme position, not from the mean position. This is the first type of the damping, which is the light damping. Now, number two, it is called critical damping. Okay. Suppose pendulum is displaced from the mean position, it is released and stopped exactly at mean position. Only 1/4 part of oscillation is completed. Side se choda, mean position रोक लिया, 1/4 of the oscillation is completed at mean position. Not half, not 3/4, not complete, only 1/4 of the oscillation. So this type of the damping is called critical damping. 1/4 of the oscillation is completed. But the problem is, when you will stop here, due to momentum mv, right? Initial momentum of this pendulum bob is mv, and finally it becomes zero. Due to this change of momentum, force is exerted. That's why the stopping object will move later other side of the mean position. मतलब अगर हाथ से आप इसको stop करते हैं तो आपका हाथ हिल जाएगा, and then you will bring it back to the mean position. So this is the problem with this critical damping. We can't stop exactly at the required location, required position due to the change of momentum. Yes, the object which is stopping, it vibrates, it goes towards the negative displacement, and then it is brought back to the equilibrium position. So this is critical damping. So we can't apply any equation here. The third one is heavy damping. If the resistive force or forces are too large, then damping may be heavy. Look, 1/4 of the oscillation is not completed. It is stopped before 1/4 of the oscillation. So this is called heavy damping. So these are the three types of the damping. One is the light damping, in which several oscillations are completed before coming to rest. This is the critical damping. Only 1/4 of the oscillation is completed. And this is the heavy damping, in which even 1/4 of the oscillation is not completed. It is stopped before the mean position. Okay, in light damping, if the resistive force increases further, then the light damping increases, time period will remain same, but the amplitude decreases further gradually. So this is the new graph. No change in time period, no change in frequency, and so on. And this is called increased light damping. Now, if the object is oscillating, this is the pendulum. How can we achieve this increased light damping? Increase the surface area of the bob, keep the mass constant, make it flat. इसको बेटा press कर दें, इसको flat कर दें. So when the surface area will increase, mass will remain same, length will remain same, no change in the pendulum. Due to the larger mass, resistive force becomes large. So more loss in the energy, so more decrease in the amp. So we can increase the light damping by increasing the surface area of the object, but keeping its mass constant, because with the change of the mass, omega changes, frequency changes, time period changes. So if we keep the mass constant, then time period, omega, frequency will remain same. And number two, if the surface area is difficult to change, then we can increase the humidity, we can increase the density of the air. In the humid air, the density of the air increases, so more density, more air resistance, because air resistance is 6 pi eta RV. So this eta is the viscosity, which depends on the density, which depends on the resistivity. So when humidity increases, viscosity increases, resistive force. So number one, by increasing the surface area, and number two, by increasing the density of liquid or gas in which the object is oscillating. These are the two ways in which we can increase light damping of the oscillating system. Now, there is a third method, and that is called electromagnetic damping. This is also the increased light damping. For example, here is a helical spring, good quality spring. a copper plate is connected with it, and suppose this line is considered the reference line, the equilibrium line. When this pulled down, when this object is pulled down, suppose at this position, then the displacement from the mean position is this. When it is released, it moves up and down, up and down. Gradually, amplitude increases. It's a light damped system. So the oscillation of this copper plate will be light damped, amplitude gradually decreasing. Look, more than one oscillations are completed. So we can call it light damped system. Now, suppose we place here a magnet. It's North Pole here, it's South Pole here. Okay. This copper plate is against pulled down to the same displacement and then released. Then what will be the graph for this? Look at the graph. It is displaced from the previous position. Mass same, so time period same. But now amplitude decreases further and it stops quickly. This is also the increased damping. Now look, copper is a metal which is not attracted by the magnet. Number one, copper magnet से attract नहीं होती. तो फिर क्या हुआ? तो सबसे पहले देखें, when it is pulled down, there is an energy stored in it, which is 1 by 2 m x naught square omega square. This is the only energy kept by the spring by the displacement. When this plate oscillates up and down, the magnetic field of the magnet is cut by the plate, and according to your O-level concept, when wire, when coil, when conductor cuts the varying magnetic field, EMF is induced in it according to Faraday's law, which is called electromagnetic induction. So we will write according to Faraday's law, an EMF is induced in the copper plate due to cutting off magnetic flux of magnet. Now this EMF has two polarities, one due to upward motion, other due to downward motion. So if the object, if the plate is moving up, so positive EMF is induced. When it's moving down, negative EMF is induced. It means the polarity of the EMF is changing. Now, the copper is a good conductor. It has low resistance. According to Ohm's law, V directly proportional to I, due to EMF, current is induced in the copper plate. And this current is also plus minus. One side it's positive current and the other side it's a negative current, but the current which is induced at the surface, for one oscillation it is moving in this direction, for the other it's moving in this direction, so it's a negative. Look, positive and negative currents are induced at the same plate. There's no outlet, there's no circuit, so both currents, positive and negative, positive I and the negative I at the surface of plate are neutralized. Positive and negative currents are neutralized in the form of light and heat, because the spark will be produced. Because the spark is produced. And spark is the loss of energy in the form of light and heat. Now, according to law of conservation of energy, right, one form of the energy is converted into the other form. So the energy which is kept by the spring is this energy. Now here, due to this oscillation in front of the magnet, it is lost as light plus heat. In the absence of the magnet, it was lost only, right, to overcome the air resistance. Now, it is lost in three ways: in overcoming the air resistance, due to the spark light and heat. When more energy is lost, right, according to the relation E directly proportional to amplitude square, when more energy is lost, more decrease in the amplitude, and this type of the damping, which increases the light damping with the help of the magnet, with the help of the electromagnetic induction, is called electromagnetic damping. So this is the example of electromagnetic damping.